Today we're looking at both rectangles and rhombuses. We have their definitions, their properties, and a few examples as well. So here's our definition. A rectangle is a parallelogram with four right angles. Right? You can kind of look at the shape here and say, yeah, it is a parallelogram. The top side is parallel with the bottom, the left is parallel with the right, and so on. So we're going to review what those properties of a parallelogram are, because we saw this in the previous section of notes, day 3. If a rectangle is a parallelogram, then it should have these properties as well. So we've learned that both pairs of opposite sides are parallel. That makes sense. You can visually look at it, and yeah, top is parallel with the bottom, the right side with the left side. Okay, what else? Both pairs of opposite sides are congruent. Yes, we expect in a rectangle the top side is congruent with the bottom side and the left side with the right side. We've also seen that both pairs of opposite angles are congruent. Well, in this case, we know that there are right angles. When you consider those opposite angles, of course they're congruent. They're both right angles. That makes sense. In a parallelogram, we learn that the consecutive angles are supplementary. That means they add up to 180 degrees. Sure enough, a right angle plus a right angle, 90 degrees plus 90 degrees adds up to 180. That makes sense. The last one now has to do with the diagonals. The diagonals bisect each other. And what we mean by that is each diagonal is cut in half by the other. So that means you have a midpoint right there in the middle. So it turns out that with our rectangle, with the four right angles, it brings along another property as well. So what we see happening here with the rectangle that did not occur in the parallelogram, first of all, the four right angles. And second of all, the diagonals are congruent. Because of the four right angles, it makes the left and the right side perpendicular to the bottom. So when you draw the diagonals, they have to be the same length. So diagonals are congruent. So that's unique to the rectangle that we did not see in the parallelogram. So let's focus on these interior angles. We want to focus more on the inside than we do the outside. When you're in elementary school or preschool, you spend a lot of time learning about shapes and all that, but now we're really focusing on the characteristics on the inside. So take this next diagram. Let's draw ourselves our diagonals. So I'll just use a ruler there to neaten it up a little bit. And those right angle symbols. Let's see what we can determine here. Okay, so if you take a look at any one of these corners, here at this vertex we have a right angle. You have these two angles. Let me number them off as angle 1 and angle 2. Notice that's a complementary pair. So one thing we notice is the measure of angle 1 plus the measure of angle 2 has to add up to 90 degrees. Another thing that we notice here is that we have lines of symmetry. We did this back in Unit 2. It's been a while. If you draw a vertical line of symmetry, that means you can take the left half and reflect it over that line of symmetry to the right half. It maps onto itself. So this top left corner touches this top right corner. This angle here touches this angle. Hey, that means they must be congruent. So if this is angle 1, this is also angle 1. If this is angle 2, we'll find that same angle here as well. So you can see that we have some symmetry from left side to right side. We also learned that there's a line of symmetry running through the center horizontally. That means the top can be reflected to the bottom. That means if this is an angle 1 at the top, then it will be the same size here and here as well. So this is angle 1, this is angle 1, this is angle 2, this is angle 2. So look at the pattern. You have 4 angles that are all this size. We're numbering them off here as angle 1. So angle 1 shows up 1, 2, 3, 4 locations. Angle 2 shows up in 4 locations. And the right angle also shows up in 4 locations. There's 4 of each kind. So we're going to use that pattern to quickly, hopefully we can get quickly at filling in all of these angles by working with specific values. So for example, if we have a rectangle with the diagonals drawn and we have one angle that's 30 degrees, do you know what the other angles would be? Can you find the other 30-degree angles? We'll use your line of symmetry. If you were to reflect the right side over to the left side, this angle that's 30 degrees at the top will also be found here on the left side as well. If you use a line of symmetry running horizontally and you reflect the top side to the bottom side, then that means we have these angles that are all congruent. 30 degrees, 30 degrees. Notice that's the same pattern that we saw here with the angle number 1. 2 on the top, 2 on the bottom. So 30 degrees are 2 on the top, 2 on the bottom. Again, each of these are right angles on a rectangle. We know it's a rectangle. They said so. So that means these have to add up to 90 degrees. So 30 plus what is 90? We need 60. So can you find all the angles that are 60 degrees? Again, if you use your line of symmetry, you can reflect the right side to the left side. So the 60-degree angle is also found here. And sure enough, 60 plus 30 adds up to 90. You can take the top side and reflect it to the bottom side. So that means this 60-degree angle shows up here. Sure enough, 60 plus 30 adds up to 90. 60 degrees is here as well. Right, so you can very quickly find what those angles are by using your lines of symmetry. Now we're going to go one step farther, and that is we want to take a closer look at what's happening on these 4 angles around point E. I don't really have any numbers here, but we can find these as well. In this case, we're not using a line of symmetry. Instead, we're going to use the triangles that we have. I could pick any triangle, it doesn't matter which one. So I'm just picking this one at the top. So if you think about this triangle right here, and you ignore the rest, you might remember that with a triangle, all the angles have to add up to 180 degrees. So we can set up a little equation here. 30 plus another 30 plus my unknown angle has to add up to 180. Right? So when we solve for that x, we'll get a result of 120. Right? So 120 plus another 30 is 150, plus another 30 is 180. So that's a 120-degree angle above point E. And guess what? This is also 120 below point E because we learned vertical angles are congruent, so they have to be the same size. Or you could use this triangle on the bottom. Those angles must also add up to 180 degrees. So now take a look at the triangle on the left and on the right. It's the same idea. Those 3 angles should add up to 180 degrees. Or you have another option. You could use a linear pair, right? So this diagonal is going to be the straight line, and here we have 2 adjacent angles, which means a linear pair is also supplementary. These should also add up to 180 degrees. So 120 plus 60 adds up to 180 degrees. So coincidentally, you have a lot of 60s over here in that triangle. But at that 60 on the left, this is also 60 on the right because vertical angles are congruent and those angles are opposite each other. Those are vertical angles. So let's take a look at example number 1. Here we're only finding some angles and some segment lengths. Let's see what we have here. We do have a rectangle, so we do know we have right angles everywhere. And the diagonals intersect at point T. T is the midpoint. We're also told that angle RPS, there it is, RPS is 62 degrees, so that's already on the diagram. But this is not on the diagram. QS is 18, so the length of the diagonal is 18. If you have a midpoint, then that means you have 9 and 9. So part A, can you find the measure of angle QPR? There's Q at the top right corner. There's P. There's R. So we're talking about this angle right here. Yeah, that'll be a complementary pair. They add up to 90 degrees, right? So we can say 90 minus the 62 degrees, and that difference gives me the result of 28. Yeah, so that's 28 degrees right there. Put that on your diagram. You might need that number on a future step. The length from S to T is 9. The length from P to R is 18. How do we know that? There's no numbers on this diagonal. Well, the diagonals are the same size. So if this is 18, the other one is also 18. And we want the measure of angle PTQ. PTQ. T is the vertex. We're talking about this angle right here. Notice that's in the middle. So we have to use this technique that we saw earlier. We're going to look at this triangle on the top and add up those 3 angles to 180 degrees. So here's the outline of that triangle. So So we have to add up these three angles to 180 degrees, but this is missing. So how many degrees is that? Well, it's also got to be 28 degrees because, again, with your line of symmetry, you can reflect the left side to the right side. So if it's 28 in the top left, it'll be 28 degrees in the top right corner. So what we're saying is we can go 180 degrees, subtract the 28 degrees from the left-hand side, subtract the 28 degrees from the top right corner, and that difference will give you the third angle. In our case, that's 124 degrees. They add up to 180. All right, so there's some examples with rectangles. Let's jump ahead to rhombuses now. So flipping ahead, we're looking right here where it says definition of a rhombus. Our definition is a rhombus is also a parallelogram, but it's a special kind of parallelogram. It's a parallelogram with 4 congruent sides. We usually put the same tick mark on all 4 sides just to illustrate that. Now here you can see that we have it sort of oriented up and down. It could be rotated. It could be presented in a slightly different way, but it still has 4 congruent sides. So that's our rhombus. But because it's a parallelogram, it turns out that all of those properties show up here as well. So this is the same list as what we saw on the previous page. Both pairs of opposite sides are parallel. Yes, opposite sides are parallel. Both pairs of opposite sides are congruent. Well, yes, that makes sense. I mean, all 4 sides are congruent, so yes, those opposite sides are going to be congruent as well. So that is true. Both pairs of opposite angles are congruent. This might be harder to see, perhaps, but again, if you use a line of symmetry that goes up and down, you should be able to see that the left angle flipped over to the right side would map to itself. They match up. So the left angle and the right angle are the same size. They are congruent. And if you have a horizontal line of symmetry, you can reflect the top side to the bottom. So the top angle matches to the bottom angle, so they are a pair that is also congruent. Now, these are not right angles, of course, because it's not a rectangle. It's a rhombus. And the consecutive angles are supplementary. So we don't have numbers here, but the concept is you could add those together, and they would still add up to 180 degrees. Lastly, the diagonals bisect each other. Yes, they do. If we draw those diagonals, you have a midpoint right there. So the left and right halves will be the same size. The top and bottom halves of that vertical diagonal will also be the same size. So all of those same properties show up here. But because it's a rhombus with 4 congruent sides, we have a few additional properties that are unique to this figure. So first, 4 congruent sides. That's part of the definition. Secondly, the diagonals bisect, yes, the diagonals bisect each other, that's true, but I'm not trying to say that. The diagonals are perpendicular, so that means you have a right angle symbol there. You could put it in any of those triangles. That means each of these triangles happens to be a right triangle. So that's a curious feature of a rhombus. Thirdly, the diagonals, they bisect the opposite angles. So let me illustrate what that means. That one's a little bit of a weird phrase to wrap your mind around. So let's use some numbers. Here's a quick sketch of 2 rhombuses that are the same size. So let's say for a moment that in this first rhombus, remember the opposite angles are the same. So let's say you have an angle that's 40 degrees at the top. You must also have a 40-degree angle at the bottom. So the diagonals are going to bisect that angle, but because the angles here and here, they're opposite each other, it's bisecting both of them. So when we draw that diagonal, it's going to split that 40-degree angle into a left half and a right half. What that means then is that you have, in this case, 20 degrees on the left and 20 degrees on the right. 20 degrees on the left, 20 degrees on the right. That's what we mean. Those diagonals are going to take that large angle, split them in half into 2 equal halves. Or if you have 2 equal halves, you can add them together. 20 plus 20 creates that big angle of 40. That's also going to be true with the angles on the left and right side, but I won't go to any numbers right here. We'll use the next example to illustrate that. So let's see what the pattern is. Given that these are rhombuses and they're the same size, that means their angles will be the same size. We've learned that we have a right angle here because perpendicular lines form a right angle, and that's one of our features. The diagonals are perpendicular. So we'll come back to that triangle in a moment. We learned that the diagonals bisect opposite angles. So this is the right half. That means the left half of the top angle is also 35 degrees. So again, this is also 35 degrees and 35 degrees on the bottom. That's the pattern we just saw previously. Now let's add that together to create this big angle at the top and this big angle at the bottom. So 35 plus 35 will make it 70 and 70. Now we have a right triangle, and we know that in a right triangle, in each triangle, the three angles add up to 180 degrees. So we can work out what this missing angle is. So we can go 90 plus 35 plus something has to add up to 180. And we can work that out and figure out it's 55. So you can check. 55 plus 35 is 90. Add another 90, get 180. So if the top half is 55, then the bottom half is also 55 because that diagonal takes the large angle and cuts it in half. You have a top half and a bottom half. So when you add that together, 55 plus 55 is 110 degrees. That's what you see here on the right-hand side. 110 cut in half, that's your 55 and 55. So again, you have a line of symmetry here. You can reflect the right side over to the left-hand side, which means this is 55 and 55 as well. You add those up and you get 110 here on the left-hand side. So notice that those consecutive angles are supplementary, right? You could pick two angles that are side by side, and sure enough, if you were to check your math and add them up, yes, they do add up to 180. We can see that those consecutive angles are supplementary. Now, we might not see that here with this diagram with these half-sized angles. That's why we had to add the left with the right side together to get the total angle, to see how those consecutive angles add up to that number. We're going to need that pattern for the example down here. So let's do example 2, and then we'll finish up. So we have a rhombus. They tell us so. We have a little bit of information. This angle at XZY, there it is. That's the 34-degree angle that they gave us. They're telling WV is 7. WV, there's the 7. V to Z is 9, so V to Z is 9. So let me put that on there. That's a 9, that's also a 9. If that's a 7, that's a 7. So before I start answering the questions, use the pattern to fill in these angles. If this is 34 degrees, can you find all the other angles that are also 34 degrees? It should be here on the other side of the diagonal. This is your line of symmetry, so reflect that to angle X. So you also have 34 degrees up here and here. We also know that we have perpendicular diagonals, which means that our triangle here, those angles should add up to 180 degrees. We can figure out what this missing angle is. Right? 180 minus 90 minus the 34 gives me this missing piece. That turns out to be 56 degrees. So this is also 56 degrees. This is also 56. This is also 56. Right? We have a lot of information here. We can probably start answering some of these questions. So part A asks for the measure of angle WZV. So there's W, there's Z, there's V. So we're looking at the top half here. That's a 34-degree angle. The measure of angle ZVY. There's Z on the bottom left, V in the middle, Y on the bottom right. So we're talking about this angle right here. That's a right angle, because the diagonals are perpendicular. The measure of angle ZYV, there's Z, there's Y, there's V, so we're talking about this angle here. Yep, that's 56. We already have that filled in. So this is a strategy. You can often fill in the angle measures pretty quickly using these patterns, and then you go back and answer the questions later on. Here we have the measure of angle XYZ. So there's X, there's Y, there's Z. So notice that's talking about this entire angle here that extends to X and extends to Z. So we have to add these two together. So we have to sum up 56 plus another 56 412. So that's the total size of angle y, the big angle y. Okay, so we have a couple of segments to take a look at here. Part E, we're looking at the length from W to Y. There's W, there's Y. That's the distance across. That's the diagonal. So 7 plus 7 will be 14. And lastly, we're looking at part F, which is from Z to W. And I don't know what that is. I don't know what any of those sides are. We know it has to have 4 congruent sides, but we don't have anything. This is the one you got to watch out for because it's not 9, it's not 7, because those are on the inside. We want the length that's on the outside. And the trick to solving this problem is to use this right triangle. You can see I already have it outlined. So let me redraw it over here so that we can just focus on the numbers that matter. Here's the W at the top left. There's the Z at the bottom right. There's V, which is your midpoint, and there's your right angle. We know that this side of the triangle is 7. We know this side of the triangle is 9. We're trying to figure out this length here, right? That's what we want to know. Well, if you have a right triangle, you might remember something called the Pythagorean Theorem. If a triangle is a right triangle, then a squared plus b squared equals c squared. And remember that the C must always go on the hypotenuse. The hypotenuse is opposite the right angle. So there it is. That's the side we've defined. C is the variable we need to solve for. So plug in these two numbers for A and B. So we have a 7 squared plus 9 squared equals C squared. It's 49 plus 81. They add up to 130. That equals C squared. But we have to get C by itself. So to get rid of that power of 2, you take the square root of both sides. And so my length is 11.4, and if we round, it still rounds to 0.40 with 2 decimal places. So every side is the same size of 11.4.